It is only in the last 100 or so years that humankind has understood that the nucleus of the chemical elements is not always fixed. It can change spontaneously from one element to another. The name for this process is radioactivity. You probably already know something about the nucleus. It's much tinier than the atom. It's made of particles called protons and neutrons. There are electrons orbiting around it. And though the atoms can share or swap electrons when they bond together, the nuclei themselves never change. Right? Well, no. Certain nuclei are not stable in that way. This means they may change suddenly, spontaneously. The radioactive nucleus flings out a small particle and transforms into another element, just like that. For example, a carbon nucleus can eject a fast-moving electron and turn into a nitrogen nucleus. There are two different particles that can be emitted from radioactive nuclei, though never together. The very fast electron is known as a beta particle. If you know a little bit about electrons, you may be thinking, what was the electron doing in the nucleus in the first place? The answer is that a neutron in the nucleus spontaneously changed into a proton, which stayed behind, and an electron flew out as a beta particle. This is not what chemistry has taught us to expect. The nucleus is supposed to be stable. Neutrons don't change into protons, except sometimes they do. The other particle that emits spontaneously from an unstable nucleus is alpha. An alpha particle is 8,000 times more massive than beta, and it's a bit slower. Alpha is made from 2 protons and 2 neutrons. If we trap a lot of alpha particles together, we get helium gas. Alpha is a helium nucleus. Like the beta particle, we would not have expected a heavier nucleus to throw out helium. But again, it happens, and the nucleus becomes a new element. So, is radioactivity useful or just dangerous? Wherever you are sitting, it is quite likely that there is a device nearby which contains a source of alpha particles, a smoke detector. The source is radioactive americium. You are totally safe from these alpha particles, which cannot travel more than a few centimeters in air. Beta particles penetrate much further through materials than alpha can. Radioactive atoms are used in medicine as tracers, to show where chemicals travel in the patient. Beta particles are emitted and have enough energy to emerge from the body and be detected. There is a third type of nuclear radiation, gamma, which is not a particle at all. It is an electromagnetic wave, like microwaves or light, but it is actually 1,000 times more energetic than visible light. Gamma rays may pass right through your body. Gamma is used to zap the bacteria in fruit to increase its shelf life, or in radiotherapy to kill cancer cells. Radioactive substances get hot, and this heat can be used to generate power. This heat has been put to use in space probes and, in the past, in pacemakers for hearts. The more abruptly nuclear radiation is slowed down, the more damage it does to the atoms it hits. This is called ionization. Alpha causes the most ionization as it crashes into other atoms, and gamma the least. For humans, the most serious effect of radiation is the damage that it can cause to our DNA. Although alpha cannot penetrate your skin, if you inhale or ingest a radioactive nucleus, the health consequences can be severe. Radioactivity is both useful and deadly, but it is all around us as a background to the natural world.
Okay, first thing I want to explain. When they showed the picture of the alpha particle bouncing around right here, hitting these atoms and particles shooting off, ionization means anytime an atom is stripped of electrons. So alpha particles can hit atoms hard enough and knock electrons loose. That's not really that bad considering what gamma can do to us. So it's confusing when it sounds like alpha is kind of the worst type of radiation. That's not what he means. Alpha particles, if you go back to the part with the smoke detector, okay, right here, alpha particles stop after a few centimeters in the air. So alpha particles, you know, if I was like shooting you all with an alpha gun, really wouldn't even reach you. And if the alpha particles did reach you, your clothes would stop the alpha particles. But if I was to shoot you guys with a gamma ray gun, that would be terrible for you, and that could cause cancer because the gamma can go right through you. Clothes aren't going to stop, it's going to go right through your body. Kind of like x-rays, sort of, okay, or ultraviolet. radiation. It's really not, UV is not as bad, but it would go right through you. So gamma is much worse for the body than alpha is, because again, our clothes stop it. So I just want to clarify that. We're going to talk about the penetrating power. So again, back to this picture with the, let's see, where was it? The one with the piece of paper. There it is, right here. So the alpha particles, nope, the alpha particle, go back.
Beta particles penetrate.
Okay, alpha particle hits the paper and bounces off, right? So alpha would hit this and bounce off. But beta would go through it. Okay, beta would go through it because it's more penetrating. Alpha is the least penetrating because it's big, right? Think about, you know, like trying to put your finger through your skin. It doesn't work, okay? But a needle would go right through your skin easily because the needle's small. Same concept. The smaller the particle, the more penetrating. So we'll talk more about that today. So it's a really good video. It kind of summarizes a lot of things about radiation and nuclear chemistry, and they can be useful, but a lot of times radiations can be dangerous too. So yeah, I just wanted to go through that again. It's a good video. Now we're going to take some notes, but first, go to table O. Go to reference table O. Let me zoom in here. So I just want to show you all these symbols here, okay? So you got your 3 types of radiation from the video. You got alpha particle right up here, 4/2He. If you take enough, put enough of them together, it's helium gas, because it's helium, but it's a little different than helium. Beta, 0/-1E. Gamma radiation, 0/0 with that weird little, looks like a Y almost. And then down here at the bottom, he didn't talk about it, but positron's another form of radiation. 0/+1E, that's positron. So those are right there for your reference, I guess, on the reference table. Oh, so just don't forget that. That's where those particles are. The one thing I do want to explain right now is how to read this. This is really important. Does anyone know what the top number stands for? So like the 4, 0, 0, 1, 1, 0. What's the top number stand for? The what? Okay. Seth? It's the mass. Yeah, just the mass. Not really atomic mass, but mass. So the mass is on top. So out of all those particles on that screen, on that chart, who's the most massive? Who has the biggest mass? Xavier. Alpha. It's got a mass of 4. The smallest mass are kind of, there's 3 of them with a 0, right? Beta, gamma, positron have a mass of 0. They actually do have a mass, but it's ridiculously small. I don't know it off the top of my head, but it's like times 10 to the -34. You know, it's like 0.0000000. A lot of decimal places. So very, 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 very small mass. So alpha's the biggest. Beta, gamma, positron are very small. Okay. What's the bottom number tell us? What's that bottom number tell us? Taylor, what do you think? What's that bottom number tell us? Well, a couple of them, they show it. The beta and the positron show what it is. What's the bottom number have next to it for beta and positron? No, beta and positron. The bottom number, what's next to it? Right, the other side. No, the left. Sorry, I'm not trying to confuse you. If you look at the 1 for beta, what's next to the 1? On the left side. For beta part. Negative, very good. What about positron? Positive, right. So what are those? What do we call those? Someone besides Taylor. Sorry, thank you. What do we call those? Charges. The top number is the mass, the bottom number is the charge. You need to memorize that. And don't write it on your reference table, that's cheating. Don't write it. On regents, you don't have that. So, mass, charge, mass, charge. So, what do you notice about gamma? What's the charge of gamma? Neutral. Yes. Positron, positive. Gamma, neutral. Beta, negative. Alpha is a positive 2. They don't put the plus sign there. It's a little bit frustrating for me. That's a positive 2. They don't put the plus sign. Just like a proton is positive 1 on the bottom. They don't put the plus sign. I'm not entirely sure. I guess I kind of know why, but they should put it in there, +1, +2. So why am I spending all this time? Because you need to know how to use this chart. And it's going to help you down the road, okay, the rest of this week, you know, when we're using these particles to talk about, all right? So those are your forms of radiation. I'm going to turn this off now. Let's take some notes. Bree, can you get the lights, please? All right, so last week we talked about what? What's the only thing we wrote down? We wrote down like one statement.
Nuclear chemistry.
Right, what else?
Unstable nuclei emit radiation and turn into a new nucleus.
Right. Unstable nuclei emit radiation to become more stable. They turn into a new isotope. Nicole, what's that called? When one isotope turns into another. Starts with a T.
Yeah. Transmutation, right, transmutation. Transmutation, that's the word, that's the key to remember there. Add this underneath that. Why are these isotopes unstable? And what are these isotopes called? So unstable isotopes, also known as radioisotopes. Unstable isotopes, also known as radioisotopes, are unstable because they have a neutron to proton ratio greater than 1 to 1. I hope your reference tables are still out, so we need reference table N next. So neutron to proton ratio is greater than 1 to 1. So 1 to 1 means really stable. Any bigger than 1 to 1 starts to get more unstable. So I'm going to explain this a little bit more. We'll come back to that. Elements 84 and up are radioactive. Except that's very confusing. Go ahead and write it down. I'll explain why that's confusing. Elements 84 and up are radioactive, and that's for the ones on the periodic table. So I should probably put that in parentheses. On periodic table. Oops, where's my O? On my periodic table over there, we can see who's number 84. Right there, number 84. What's that? What's it called? Anybody? Oh boy. Polonium. So polonium 84 all the way up to 118, which is right here, that these are on there. And all these down here too. A lot of these are radioactive, even the 58 through 71, but down here, 90 through 103, all the way up here, are radioactive. However, this is confusing. Here's why. Go to table N. Ryan, do you have any money you want to rub on top of my water bottle?
I got $3.
Maybe after class.
Alright.
If you go to table N. Oops, went the wrong way. Look at the top of table N. See where it says nucleate, top left. All that means is the nucleus. Why are you getting that now?
Because we're using it. We know I need it.
I feel like I just spent 10 minutes talking about table up.
Saving what?
Oh, it was up here. You were looking up here,
Yeah,
but
I
I
was
wanted you to
looking at
look
it.
I wanted you to have it in front of you.
Yeah, but it was up there so I can see it.
Just next time I say get it out the first time.
Yeah, no problem.
So table N, the nucleate is just the nucleus, the element. So if you look at the first one, 198 AU, the way you say that is gold 198. Look all the way to the right, it says nucleate name, so gold 198. Okay. Look at the one underneath it, carbon 14. What atomic number does carbon 14 have? What atomic number does carbon 14 have? 14 is the mass number. All those numbers on table N are mass. So what's the atomic number of carbon 14? 6. Look where 6 is, over here. It's way below 84. But guess what? Carbon 14 isn't on the chart. That's carbon 12. So that's why this is sort of confusing, but not really. On the periodic table, 84 and higher, those are radioactive. But all the elements can, I don't know if they all do. Actually, I don't know. Sorry, I don't know. But all of them can have radioisotopes. It's just not the one on the chart. So if you keep going down, table N, find nitrogen 16. Find N16. That's radioactive. The one on the chart is nitrogen 14, not radioactive. Let's explain why, even though it's written right here. So let's do this. I want you to write unstable and then stable. And we'll pick a couple. We'll do carbon 12, which is C12 over 6. Oops, that's in the wrong spot. Sorry, that goes here. Carbon 12, C12 over 6. It has 6 protons, 6 neutrons. When you subtract 12 and 6, you get 6, right? So it's a 1-to-1 ratio. Over here, carbon 14, it's 14 over 8. So that's 8 protons and 6 neutrons, right? So it's not 1-to-1. And depending on how you look at the ratio there, oops, what did I do wrong? I don't know why I did that.
I wrote it in pen, so.
I know. It might
What
be
did you
the
do
end of
wrong?
your day. What did I do wrong?
I think what you did was you put 6 neutrons.
Well, that's wrong. This. Sorry.
Alright, I can wrote that down yet, so you're.
I don't know what. I had all the 8s and 6s backwards. So 6 is the atomic number. When you subtract that, you get 8 neutrons. So the ratio is not 1-to-1, it's unstable. So I'm using this as an example of what this means. This is unstable, this is not. However, another good example, the big ones at the bottom are very radioactive. Uranium-238 is a good example. Uranium's radioactive. I feel like you knew that before you got to chemistry. U-238 over 92. That's right over there on the bottom, number 92. So 238 over 92, it has 92 protons. If you subtract 238 and 92, you get 146 neutrons. So one reason uranium is unstable is because it doesn't have a 1-to-1 ratio of neutrons to protons. The other reason, okay, you want me to write it higher? Steph, are you good?
No.
All right. Shelby, can you see this?
Yeah.
I'll just rewrite it. 238 over 92, 92 protons, 146 neutrons. So besides the fact it's not 1-to-1, here's the thing about nuclei. The nucleus of carbon and the nucleus of uranium are the same size. So imagine this room is a nucleus, and we have 12 people in here versus 238. 238 would be very crowded. So part of the reason at the bottom of the chart they're all radioactive is because the nucleus is so crowded. So what does it do? It emits radiation. It emits radiation to try and make some room. So imagine we had 238 people in here, and we picked a select few to throw out the window to make more room. You know, I think I could think of at least one person. But so we throw them out the window. Why are you guys laughing? You don't know who it is. Anyways, that's what radiation is all about. The nucleus is unstable, so it tries to get rid of some of that energy, we'll call it, the particles in there, to make more space, to be more stable, right? So that's hopefully helping you understand a little bit. Next thing I want to do is talk about radiation, specifically. Can anyone give me a definition of radiation? You know the 4 types: alpha, beta, gamma, positron. Can anyone give me a definition of radiation? Zach, go ahead.
I really don't.
Well, you didn't really try. You gotta give me a little something. So you know what they are. Alpha, beta, gamma, pi. Those are the four. Where do they come from? What was that video showing? Where was the radiation coming from in that video?
The sneezing.
The sneezing. And what did, I'll come back to you, someone can help you. What were the little waving faces, what were they supposed to be? I don't know, what'd you say? The stuff, yeah, that one they showed the wave, that was gamma, but the actual ball itself, what was it supposed to be? It had an N on it, a C on it, a AM. What were the little characters, what were they supposed to be? They weren't atoms. They were nuclei. They were the nucleus. So where's the radiation coming from? The nucleus. So we're halfway there. So radiation, and what is it? Is radiation, Zach, is it a particle or is it a wave or is it both?
It's both.
Good. Radiation is a particle or wave. Now it's coming from the nucleus. Let's come up with a fancy word that he probably used. It's not fancy, but it starts with an E. You don't use this in regular. Yes, emit. You don't really talk. You don't use the word emit very often in normal conversation. A particle or wave emitted from the nucleus of, but it has to be a nucleus of what? So like this water bottle is not giving off radiation. Why? It's not unstable. So particle or wave emitted from the nucleus of an unstable nuclei. Nuclei. Or we could say radioisotope. Radioisotope. And that's basically the definition of radiation. Particle wave emitted from the nucleus of an unstable nuclei or radioisotope. And I do want to also add here, heat is produced as well. But I don't know if that is produced every single time radiation is emitted. I really don't, but I know it's common. So I'm not going to tell you something 100%, and if I don't really know for sure myself. But heat, it's common for things to heat up. Has anyone ever known anyone that had a tumor and they blasted it with radiation to try and kill the tumor? Know anybody? Okay, one person? All right, well, my dad, a long time ago, had radiation therapy, and the skin around and the actual spot of the tumor would get, like, you could feel it. It would be hot and it would be red. So I use that as an example that this does happen, okay? Radiation will create things, create heat, will get hot because of the radiation, whether it's being emitted and it's getting warmer or it's hitting something and getting warmer. But anyways, that's radiation. Now, last thing I want to end you with here, we got a few minutes. I want you to draw a little box here on the left side of your paper. It's called a radioactive source. And then we're going to draw somewhere on the right side 2 plates. One's positive, one's negative. And going through the plates are going to be radiation. So this is going to be emitting radiation. I'm going to draw 4 arrows. You are going to label which arrow is which type of radiation. So alpha, beta, gamma, positron. So here we go. So one's going to go straight through. One's going to go up here. So there's 1, there's 2. One's going to do something like that. You know what?
No.
I just want to bend it a little bit more. Okay. So there's 3, and then 1 more, and it's going to kind of do this. 4. It doesn't have to be perfect. So using your chemical knowledge and chemical intuition that you are building this year, take a minute. You can label it mentally, so you don't have to cross it off if you're using a pen. But which arrow is alpha, which one is beta, which one is positron, which one is gamma? I'll give you a big hint. This is negative, this is positive, so you have to know the charges of the radiation and then see, okay, how are charges affected by negatives and positives? What if the particle's negative, or what if it's positive, or what if it's neutral? We're going to go right to the bell. Your homework is that worksheet. I sent a text out later with a link showing you a 2-minute video on how to do the last question on the homework, because we didn't have time to do it today. So I would suggest watching that so you can do that last problem. You'll get it like 2:30. If you want it sooner, I can send it again.
Yeah, do that.
All right. All right, what do we got? 1, 2, 3, 4. Anybody want to take an educated guess at number 1? Which of those 4 is going to be deflected towards the positive plate? Let me ask this question. Do 2 positives repel, or do 2 positives attract? Or how does it work with charges? Is it opposites attract or the same attract? Opposites attract. So number 1 must have what charge? Negative. What's the only one with a negative? It's the only radiation with a negative. Beta. So number 1 is 0, negative 1, E. That's your beta. Okay? So I'm just going to put B minus. Oh, and I want to talk about table N more. We'll do that tomorrow. Who's number 2? The one that goes straight through, not affected by charge. Gamma, because it's neutral. Now, 3 and 4, obviously alpha and positron, but which is which? We'll do it tomorrow.